Hello, this is Dr. Strickland. In this video, we will investigate delocalized electrons and resonance contributors. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you are ready for the more difficult things we will do together in class. So the story of delocalized electrons really begins with benzene. By the mid-1800s, people knew that benzene existed because it had been isolated from the leftover whale oil in the street lamps of London, but they couldn't figure out its structure. And in fact, it was one of the significant scientific puzzles in the mid-1800s in Europe. So what people knew from the experiments they had done was they knew its molecular formula. From that, they could calculate the degrees of unsaturation, but experimentally, they found that it would not undergo the normal reactions of alkenes or alkynes. With electrophilic addition reaction conditions, they would just isolate back the starting material that they started with. And it had a strong odor, which was how these things got to be known as aromatic compounds. Now, when X-ray diffraction was invented in the 1930s and people could take a look at experimental data that would give them bond angles and bond lengths, they found that benzene had 6 identical carbon-carbon bonds. And here's the measurement. And the interesting thing was that was shorter than a carbon-carbon single bond, but longer than a double bond. It was somewhere in between, which was weird. And it also had 6 identical carbon-carbon-carbon bond angles, 120 degrees each. So the concept of localized electrons and delocalized electrons was born. And localized electrons are defined as belonging to a single atom or being shared by two specific atoms. Basically, they're held in one location. So it can be a non-bonding pair of electrons, or it can be a sigma bond. Each of these pairs of electrons would be localized, even though these are non-bonding electrons and these are bonding electrons. In terms of like if you've got a multiple bond, a pair of pi electrons is a localized set of electrons. Sigma bond, either between the two carbons or between the carbon and the hydrogen, these are also localized pairs of electrons because each one is confined to one geographic location. But delocalized electrons are different because using rules that we're going to take a look at here in just a bit, the electrons in this little 3-atom portion of the acetate ion can move. And it's not that the atoms move. In fact, one of the rules of writing resonance contributors is that the atoms never move. But electrons move, specifically pi electrons and non-bonding electrons. So if you follow those 2 curved arrows, we've got this and we've got this. So these 3 atoms make up a delocalized system because the electrons are actively being shared by 3 or more atoms. In the benzene ring down here, I've added the hydrogens, and you can actually move them around like this. Because one of the curious things about benzene's structure was that if they drew like this, they expected to see 3 shorter bonds and 3 longer bonds, but that it wasn't what you find with the measurements of benzene at all. You find out that all of those carbon-carbon bonds are more like a length that would be appropriate for a bond and a half, which was weird. And the way that they explained it was to say, okay, maybe the electrons have some movement to them. Maybe they can be shared by more than 2 atoms. And as we'll see, benzene is an even fancier case. So resonance contributors are like these 2 things here. Let's pull this back down just a little bit. These 2 guys are resonance contributors for the acetate ion. These 2 guys are resonance contributors for benzene. Because if the real structure involves delocalized electrons, then any one representation involving localized electrons is called a resonance contributor. So, what we draw is Lewis structures, where you put electrons in particular places. We use these curved arrows to say, hey, they can move from here to here. But in any one of these structures, what we see are localized electrons. And so, for example, you can do that for lots of other things. This is nitromethane. And in nitromethane, if I move this pair of electrons down here to change this nitrogen oxygen single bond to a double bond, then I have to move something away from the nitrogen. And so this pair of pi electrons becomes a pair of non-bonding electrons on this oxygen. And in fact, when people measure the nitrogen-oxygen bond length in the nitro group, what they find is that it's about a bond and a half. It's intermediate in length between a nitrogen-oxygen single bond and a double bond. Because, of course, a single bond between two atoms is going to be longer than a double bond between those same two atoms. So the resonance hybrid is the best representation of the real structure and involves the blending of resonance contributors as a weighted average. So in this case, we would represent it like this. Now, this part of the molecule is the same in both cases. Oops, sorry, I forgot my positive charge there. But if I want to show that I've got electrons that are shared between these three atoms, what I'm going to do is draw dashed lines like that. And then the pairs of electrons, the non-bonding electrons that are there anyway, gets shown. And this gives us partial negative charges on these two oxygens. And the reason they have partial negative charges is because in one resonance contributor, it's uncharged here and it's a negative there. So it's a partial negative in the resonance hybrid. Same thing for this one. Now the nitrogen has a positive charge in both of them, so it still has a full positive. But this is the delocalized portion. And so that's where we see the electron movement. So in order to draw resonance contributors, we need some rules. So the first thing we already talked about, only electrons move. The atoms never move. Only pi electrons and lone pair electrons can move. Sigma electrons never move. The total number of electrons in the molecule doesn't change, so each resonance contributor has the same net charge. And electrons always move toward an sp2 or an sp atom. sp3 atoms can't accept electrons. So we'll see these, lots of examples that we do. But these are the basic rules, and we do them in order. All right, so that is the basic story on delocalized electrons and resonance contributors. If you have any questions, please send them to me.